A vector-valued function maps real numbers to vectors. A function of the form r of t equals f of t times the vector I plus g of t times the vector j. If there's only two, then you're in a plane. If you have a third component, h of t times vector k, then you're in three-dimensional. R of t is a vector-valued function where the component functions f, g, and h are real-valued functions of the parameter t. Vector-valued functions can also be written in component form, which this is probably a little easier to write. You have your x of t type. I'm just going to keep them labeled f, g, and h to be consistent with the textbook. The domain of a vector-valued function, r, is considered to be the intersection of the domains of the component functions, f, g, and h. So let's look at an example. We have r of t is equal to natural log of t times vector I plus square root of 1 minus t times vector j plus t times vector k. If you investigate each piece, natural log of t, remember natural log is happy as long as the t value is positive, so its domain is 0 to infinity. Square root, those are happy as long as what you have underneath are greater than or equal to 0. The numbers that make sure that this is 0 or larger would be a 1 or something smaller. So that domain is negative infinity to 1. For example, if I pick a number in here like 0, 1 minus 0 is 1, that's positive. You could take the square root of it. If I use exactly 1, 1 minus 1 is 0, square root of 0 is 0, and so that's another number that can be used. But if I jump here to like 2 or 3, 1 minus 2 or 3 becomes negative, and those don't work. The third component, t, that's good for any real number. If you look at the overlap, 0 to 1 including 1 is your overlap. And so that's the domain of your vector-valued function r of t. Sketch the plane curve represented by the vector-valued function r of t equals 2 cosine t times vector I minus 3 sine t times vector j over the interval from 0 to 2 pi. We're going to let x be 2 cosine t, and we're going to let y be negative 3 sine t. If you divide this equation on both sides by 2, you get x over 2 equals cosine of t. This equation divided both sides by negative 3 will give you sine t. From Pythagorean identities, remember that sine squared plus cosine squared t is equal to 1. If we square each of these, then that gives us x squared over 2 squared, and for the sine squared part, y squared over 3 squared. The reason I left them 2 squared and 3 squared is in the x direction, I know that the ellipse is going to go 2 units left and right of the origin, and in the y direction, 3 units above and below the origin. If you were to let t increase from 0 to 2 pi, which is the domain they give us in the beginning of the problem, I'm going to let t increase from 0 to 2 pi in this column, substituting each number in to the vector-valued function, and then putting my answers over here. So starting at 0, when t is 0, sub in, you get 2i. When t is pi over 2, you get negative 3j. So we've worked our way from 2i to negative 3j. When t is pi, we get negative 2i. So as you progressively sub in your t values, the answers will tell you which direction you're going around this ellipse. It turns out this one has a clockwise path. Sketch the space curve represented by the vector-valued function r of t equals 4 cosine t times the I vector plus 4 sine t times the j vector plus t times the k vector. And we're going to take t from 0 to 4 pi. Let x be 4 cosine t, let y be 4 sine t, and z will just be t. Like on the last problem, we isolated our cosine and our sine functions, because if we isolate sine and cosine and square them, we're going to get 1. X squared over 4 squared, which is 16. I'm going to go ahead and call it 16 for this one. I left it 4 squared in that form on the last problem. Squaring the y term, sine squared, that's y squared over 16. Multiply through by 16, and what we have is a circle centered at the origin with a radius of 4, because 16 is 4 squared. What that tells us is by using just the x and the y, then on the xy plane, which would be like your desktop or tabletop, we have a circle centered at the origin with a radius of 4. The z value is what takes us higher and higher up that cylinder, because when we take a circle but we kind of telescope it up the z-axis, we're going to get a cylinder. It's very hard to tell, but from here, this is just like a helix that's wrapping around this cylinder. As t increases from 0 to 4 pi, the point xyz spirals up the cylinder to produce a helix. If you are given parametric equations that are x in terms of t, y in terms of t, z in terms of t, then you can just directly plug those into the x, y, and z positions for I, j, and k. So don't hesitate. If you're given the parametric equations, just match them up with location. X comes first, y comes next, z last. Represent the parabola y equals x squared plus 1 by a vector-valued function. Now going the other way, where you have to come up with the parametric equations, that's a little bit tougher. Usually what is common is the independent variable x, we're going to let it just be equal to t, the parameter t. The y value will be t squared plus 1. This is very common. The independent variable will go first, and then the dependent variable y goes second. As far as your order goes, if you pick a t value like, I don't know, -2, let x be -2. -2 squared is 4, plus 1 is 5, so that's this dot. Then pick a larger t value like -1. If t is -1, -1 squared plus 1 is 2. And so you can tell that the larger you make t, after subbing in, you'll get a y value that will take you this direction around the parabola. If r is a vector-valued function such that r of t equals f of ti plus g of tj, that's for a plane. If you're in space, then it's f, g, and also h. When you need to take the limit of a vector-valued function, it's totally appropriate to assess the limit of each component separately. You'll let t approach the same numerical value, but you can isolate the f, the g, and if you have a third component, the h. Another definition of vector-valued function r is continuous at the point given by t equals a when the limit of your vector-valued function exists. As t approaches a, then that value, the limit value substituted into your vector-valued function, is equal to the vector-valued function with that numerical values directly subbed in. That's continuity. A vector-valued function r is continuous on an interval I when it is continuous at every point in the interval. Example, discuss the continuity of the vector valued function r of t is equal to ti plus aj plus a squared minus t squared k when t is equal to 0. So we're going to take the limit as t approaches 0 of our vector valued function. Each part we can assess the limit individually. Okay, so the limit of t as t approaches 0 is 0. The limit of a as t approaches 0 is a, because there's no variable t to plug in, a 0. A squared minus t squared, that's going to be a squared minus 0 squared, which is a squared. And so this reduces down to 0i plus aj plus a squared k. If you do a direct substitution, r of 0, you'll get a 0i, an aj, and an a squared k. You can conclude that r is continuous at t equals 0. Determine the intervals on which the vector valued function r of t equals ti plus square root of t plus 1j plus t squared plus 1k is continuous. The component forms are f of t is t, g of t is square root of t plus 1, and h of t is t squared plus 1. Note that f and h are continuous for all values of t. Any number you can sub in will remain the same for f. Pick any number, square it, add 1, you're going to get another real number, so those are fine. G is the only holdup because you have a radical, a square root radical. T plus 1 is greater than or equal to 0 as long as t is greater than or equal to -1. So your vector valued function r of t is continuous for any value of t -1 or larger. Remember, it's the intersection. I hope this video helps. Reach out by email, ask in class, office hours, and I'll do my best to help you out.